Hello everyone, and welcome to this second spatial interpolation lesson about kriging. My name is Ken Arroyo Hori, and I'm a researcher in the same 3D information group as Hugo. And the idea of today's lesson is to talk a bit more about this complex method. I want to do two things today. The first is to give you a brief overview about kriging in case you haven't been able to go through the material, or in case you have done it already, to highlight some important points. And the second is to show you how to do it in practice using a Python library that's called PyInterpolate. So let's get started. So first of all, let's talk a bit about what kriging is. As a very brief overview, kriging is a weighted average interpolation method, just like IDW or natural neighbor interpolation, and so on. It's a method where the weights are based on the spatial correlation between the points, which is sort of similar to other interpolation methods that you have seen in this course. And the weight is given by a custom geostatistical model that is built for each dataset. So that's the main thing in which it differs from other methods. But you might be wondering, how do I create this custom geostatistical model? And the answer is that it can be created using a variogram. So let's go through these one by one, and I think it makes most sense to understand what's going on if we do the opposite. So in terms of the data flow, we start with a certain data set. Here we have a few data points from DTM. You can sort of see that in the middle there's a higher area, and as you go like to the upper right and to the lower left, the values go down in elevation. So if you just take the data set and you start computing what are the difference between the points, like let's say between this point and this point, you will be able to figure out that there's a certain distance between them and a difference in elevation as well. When we do that for every single point in the dataset, we arrive at what is the figure on the left. So this is called the variogram cloud. And this shows you something quite interesting already. So when the points are very close, so this is the x-axis, this tells you what is the distance between the points. When the points are very close, the difference between them in terms of elevation is also very close to 0. So the y-axis is the difference in elevation that you can see. This is an absolute difference. And as you go farther away from 0, so as the distance between the points becomes larger, you will notice that this difference in elevation tends to increase. I mean, it's not a one-to-one match. You can find points that are very far away and still have a very similar elevation, and points that are relatively close to each other and have quite a big difference between them in elevation. But if we take this variogram cloud and we sort of compute the averages for different distances, we come up with what you can see here. So basically, we just computed some ranges, which in kriging in the variogram are called bins or lags. And this shows you what is the average dissimilarity in elevation between the points as you get a different distance between the points. So as the distance between the points becomes larger, also the dissimilarity between the points increases. So this is the base for the geostatistical model that is used in kriging. So we first take the data set, we compute the variogram to know what is the shape of the similarity as the distances increase. And then we create a function that sort of models the same behavior. This is usually based on a few different parameters. These are called the SIL, the nugget, and the range. The nugget is what is more or less the similarity when the distances are very, very small, so when they tend to 0. You might be wondering why you have such a value, and the answer is that even in datasets in practice, you always tend to have a bit of noise, or maybe there's some roughness, which means that the dataset, the points that are very close to each other, tend to have quite a bit of a difference between them. Or there are errors in measurement. So there are all sorts of possible behaviors that explain this. And all of these can be modeled by the nugget. Then you sort of have the range. So the range is how far do you need to go like from one point to another, so that the points do not really resemble each other. So the dissimilarity between the points tends to increase up to a certain point, and there's a point usually when the dissimilarity is just more or less the same. So that point is called the range. So the distance up to which you can still find some increasing dissimilarity between the points. Then you have the CIL. So this is the y-axis, and the CIL and the range are related. So if the range tells you how far do you need to go, like in the distance between the points, the CIL tells you how different the points get in between them. These are the three usual parameters that are created, that are modeled using a theoretical function. And we will see a few different functions in the second part of this lesson. So then we take this statistical model that we created that tells you how the points differ as you get further away, and this is converted into a sort of covariance function, a correlation function. And so whenever we want to do a weighted average interpolation, we can take the different distances between the points. Let's say that we want to obtain what is the value of the elevation here at x, and we want to figure out what is the weight that we give to point pi here, which is located at a distance of 90 meters away. And then this is the formula for a weighted average method for interpolation. And based on this distance, we can figure out the weight. And the way in which we do it differs a bit depending on the kriging method and the function that we chose to model the dissimilarity. But it can be obtained. So finally, again, we just go to the weighted average function, and we compute the value of the interpolated point, in that case x. So as you might be able to tell already, kriging is a bit different from the other methods we have seen in this course. Kriging models the correlation based on the specific characteristics of each dataset, so you don't sort of need to guess, like with IDW, for instance, what should be the power that you want to give to the function. You just model the behavior of the specific dataset, and based on that you know what is the ideal way in which the correlation tapers off. It's also different because it mathematically minimizes the interpolation error. So in theory, kriging should be the best method according to the dataset that you have. It's not always the case, but it does tend to have better behavior than other methods, especially when the datasets are kind of complex, which kriging handles very well. So if you have datasets that have noise, maybe they have irregular point spacing, so you have a bunch of points very close together and some points that are very far away with some gaps. Kriging tends to handle that better than other interpolation methods. And also it handles regular patterns very well. So as you have seen in a previous lesson, sometimes regular patterns lead to artifacts whenever you are interpolating, and kriging doesn't tend to do that as well. So going a bit into the theory behind kriging, this is the only important bit that I want to show you today. You can read more about it in the book for the course. All types of kriging follow a certain geostatistical model, and the idea is that whenever we want to estimate the value of a of a random variable, we can divide it into two sort of elements. First, the expectation or mean, and this tells you what is the overall trend in a certain dataset. And then there's the residual, which is the deviation from the trend. So you can think of it more or less as the fact that the expectation shows you sort of the large scale, the big behavior, and the residual tells you more about the local variability that you have. So in practice, what we care about in terms of kriging is that different types of kriging, of which there are many, have different assumptions in terms of what should be the expectation and what should be the residual. For this lesson, we have covered two types of kriging mostly, simple kriging and ordinary kriging. And they differ because simple kriging assumes that the expectation has a known value which is fixed, so just a value that you say it's maybe like the mean of the dataset or something, whereas ordinary kriging sort of computes it on the fly using the local mean, so the mean in a neighborhood. And yeah, I will cover both of these in the more practical part of this lesson, which comes next. So let's talk a bit about kriging in practice and how we can use PyInterpolate, this Python library, to do kriging. So PyInterpolate is a Python library for geostatistics focused on interpolation and kriging, but it also implements like IDW, among other things. It can allow you to easily plot a baryogram and to do various operations on it, like we will not cover it in this lesson, but you can do like regularization of the baryogram, you can compute like directional baryograms, you can compute many things. And PyInterpolate can help you to do that. So if you go to the PyInterpolate website, in the tutorials section, you have a bunch of tutorials that can help you learn how to use the software. Within this lesson, I want to go through two of them. The first one in the beginner section, so a semi-baryogram estimation, which tells you how to compute the baryogram. And the first one in the intermediate section, which is about ordinary and simple kriging, so how to apply it using the library. Let's go through the first one, semi-baryogram estimation. The idea of this tutorial is to read some data set, use it for semi-baryogram modeling, apply different theoretical functions, learn how to do it manually and automatically, and figure out how much error there is with different functions. The first thing you need to do in order to use this package is to import some things. So first of all, you need to use NumPy, which is used for linear algebra, like all the matrix types. And the second one is to import matplotlib. So matplotlib is used for plotting baryograms, and you can use it to plot many other things as well. And from PyInterpolate itself, it has a function to read text, sort of like CSV files and so on. Function to build the experimental baryogram manually. There's also some types like the theoretical baryogram, which can be used to compute it automatically, and some more things. So the first part in the tutorial itself, to read the point data, for this we use the readTXT function that we saw previously. I think it's using this dataset from Poland. And yeah, if you look at 5 lines of the dataset, it just looks like this. So there's an X value, a Y value, and a Z value, more or less. Using that dataset, we want to first create the experimental baryogram. So the idea is to create experimental baryogram using some parameters. So this is the step radius. So whenever we want to compute the baryogram, we need to figure out what the size of the bins or the lags should be and what is the maximum range. So usually you want to only compute the baryogram for something like half of the size of your dataset, so half of the diameter, more or less, because starting from that point it makes less and less sense, mostly because you have fewer points that are far away. This experimental baryogram that you can create gives you a few different measurements. So it gives you the semivariance, which is the dissimilarity, the covariance. So usually you take the semivariance and you convert it to covariance, because this is a measure of similarity and you want to give higher weights to the points that are close together, not lower weights. And this is the and also the variance between all points. If you print the data that you got from the experimental baryogram using the size of the lag that we just passed, we get a few different parameters. So there's the semivariance, so this is a measure of dissimilarity. So this is telling you that up to 500 meters, points tend to differ by 14.71 units in the Z coordinate. Then there's the measure of the covariance, which is sort of the opposite. So these are similar to each other, and as you go farther away, this tends to be less and less similar, and even here we have some negative values. And here it's plotting the difference between the variance and the covariance. Ideally this should be equal to this value for the semivariance. In practice it's not going to be the case, but it should be reasonably close because this is related to second order stationarity. Yeah, if it's perfectly second order stationary, then you should get the same values in theory. If we plot the experimental semivariance and the covariance, we have something that looks like this. So the semivariance goes up and the covariance goes down at the same rate, pretty much. And the variance is just one value for the entire data set. The covariance starts more or less at that value and goes down, and the semivariance starts from 0, and then it should go up to more or less that value. Yeah, so starting from that, let's try to fit a few semi-baryogram models. So these are the theoretical functions. We talked previously about the nugget, the seal, and the range. So these are the the 3 parameters that you need to set up either manually or automatically. Within PyInterpolate, you have a few different functions. So there's a circular model, a cubic model, exponential, Gaussian, linear, power, and spherical model. And yeah, we will show you more or less what these look like and some characteristics. These are some good hints on how to set the different parameters. So first, you can set the seal to the variance, just as a rule of thumb. Then I'll get to 0, and then we can see if we need to raise it in case of anything. And the range in case it's done to 8000. But I would say if you don't know anything about the dataset, just do like half of the dataset distance and like the maximum distance, and then we see. So first of all, like this is what happens when you fit the circular model using those parameters. You can tell that the circular model just goes up more or less quickly, not too much, and then it tends to level off later on up to the range. This is the results for the cubic model. The cubic model is quite different because it starts low, then it speeds up, so it has a greater slope here, and then it levels off later on. The exponential model, yeah, it's not super clear here, but the idea is that it goes up quite quickly and then it just levels off at a point. For the Gaussian model, it's a bit similar to the cubic one, so it starts slowly and then it reaches a value and it levels off at that one. Linear model is quite simple, so it's basically just a straight line starting from the nugget and then it goes up to the range, and from that point it's just flat. And this is the power model. So this is power as in what you get with IDW. As you go farther away, you assume that the similarity increases with a certain power. And finally, the spherical model, which is kind of similar to the circular one. It starts more or less quickly and then it levels off. You can notice that it's quite smooth in what happens when you get to the range. So you can do all of these computations, you can see which one fits best. So in the case of this tutorial, the idea is that the dataset was split into a part for the computation of the baryogram and a part for testing. So once you do the baryogram computation, we use the remaining points to see how good of a fit we get with different models. And the result is when we do like the root mean square error using the remaining points with the different theoretical baryogram functions that were computed. The best model in this case seems to be the linear one with an RMSE of 28. We should be able to see this if we go to the plot. So here you can tell that it is pretty close to the actual semivariances, which means it's a good fit, although you could definitely get a better fit if you start adjusting the parameters so that you get something that more closely matches the points that you get in the baryogram, in the experimental baryogram. But you do not need to do this manually. So PyInterpolate has the option to automatically compute the same baryogram model. So basically it does like an auto fitting with different models, different parameters, and so on, and then it just gives you the final result. In this case, it's choosing the linear model, but it should be able to come up with better parameters. And yeah, once we do this automatic fitting, we come up with this, which was actually closer to what we had whenever we were just putting some values at the beginning. It has some other interesting functionality. So PyInterpolate has the option to export the model. So this is a bit of a computing the variogram is a bit computationally intensive. It takes some time. You need to figure out some parameters. So once you do that for a dataset, you might just want to export the model, write it to a file, and then read it back. This is possible, and you can do the opposite. So read the model from a file so that you can reuse it. So now let's go through the second tutorial, which is about applying ordinary and simple kriging using the library. It starts pretty much as the first, so you need to import some packages and you read the point data. You separate some points from the dataset, so there's a training dataset and a test dataset to see how good the interpolation is. This is done randomly to avoid any bias. So first of all, we set the semi-variogram model, so in the way that we did in the previous tutorial, using a step radius of 500 meters, maximum range of 10,000 meters. Here you can see again the experimental semivariances, the covariances, the variance. This is converted into a theoretical model, so again linear. You compute the values, and for this you want to apply both simple kriging and ordinary kriging. And this description tells you more or less all the parameters that you need to pass the functions to apply simple kriging and to do ordinary kriging. So there are the observations, so these are the data points. Theoretical model, this is a theoretical variogram function so that it can figure out the correct weights to use for the for both functions. The points that you want to interpolate, so the locations. Whether you want to do ordinary kriging or simple kriging, this is the range. So this is kind of an optimization. So how far do you want to search for point neighbors? How many neighbors to use to estimate the unknown values. This is also an optimization, usually with kriging as with other interpolation methods. Whenever you get very far away, the value of the weight tends to be negligible. And kriging can be very slow, so it has some computational characteristics that are kind of different from other interpolation methods. So it's good to limit the search to only a few neighbors. Whether you use all the neighbors in the range or only some. In case of simple kriging, we need to know the mean. So what is the value that we want to pass through it? This is about approximate solutions, but it's not a very important thing. And the number of workers, this is just for the how many threads more or less you want to run. So for simple kriging, we only use the first four, so the first four are the most important. What are the known points, the theoretical variogram functions, the points that we want to interpolate, and whether you do ordinary kriging or simple kriging, plus the mean. So first, what mean do we use whenever we want to do simple kriging? Either you sort of know it from some physical parameter, or you compute something like the mean of the data points that you have, but you should always take into account that the mean of the points that you have is not maybe the mean in the region. Like imagine if all the points that you have are, or many of the points that you have are sort of bunched together and there are a few points elsewhere, then the mean is not going to be very representative, but it is a reasonable point to start. This is what happens whenever you do when you apply kriging. You get a prediction, and this goes for both ordinary kriging and simple kriging. So in the next part of the tutorial, the idea is to sort of use this function to compute the estimation from kriging at all the unknown locations, so the places where we want to test. And in this tutorial, we want to test at the points that we separated from the datasets, and we use them to figure out whether we have a good fit or not. Similar to the previous tutorial, we can compute the root mean square error for all of these predictions, and then we see how well simple kriging performs, how well ordinary kriging performs. And yeah, with this library, it's also very easy to do IDW, so it's easy to do that as well. At the same time, in this tutorial, the idea is to check what is the effect of different parameters. So how many neighbors do you want to use for the computation, like 4 neighbors, 8 neighbors, 16, 32, up to 256. You can imagine that if we use more neighbors, it's going to be more accurate, usually. But also at the same time, it's going to be much slower. So if you go through this tutorial and you run the result, yeah, you will see how long it takes whenever you are doing the computation. So in this case, yeah, you can also tell from the output that these first few tests with 4, 8, 16, and 16 neighbors are quite fast, so like less than a second. But whenever we go to 32, it's like 19 seconds. Whenever we go to 64, it's like 55 seconds. And the time goes up after that. So yeah, it gets much slower. At the same time, you can expect that the root mean square error tends to go down if you use more neighbors. So it starts at 3.4, then it goes to 3.29, 3.26, 3.26, 3.25, and so on. And yeah, this is usually the behavior that you can expect. So there's a trade-off there. First, as you increase the neighbors, the root mean square error tends to go down quite a bit. But there's a point at which it yeah, you get decreasing gains from just increasing the number of neighbors, and the computation times get much bigger. So this test was done for ordinary kriging first, and then it's the same for simple kriging. In this case, it's using as the mean, just the mean of the points that were given. And again, it's doing the test with different numbers of neighbors, so from 4 to 256. Yeah, there's a similar pattern. So few neighbors are very fast, more neighbors are slower. The root mean square error starts high and it tends to go down. But yeah, also something that is more or less to be expected. So simple kriging is usually less accurate than ordinary kriging. So especially with a low number of neighbors, the root mean square error tends to be quite high at the beginning. But as you go down to using more neighbors, we reach like 3.25, and you can notice that it's more or less the same as with ordinary kriging. So yeah, maybe just don't use simple kriging with a low number of neighbors. You either go for ordinary kriging or you tend to use more neighbors just to get better results. Yeah, if you want to follow these tutorials or some more tutorials, these are quite easy. So these are easy to run just interactively, just copy and paste the code that you get there. PyInterpolate is also very easy to install, and by doing this in practice, you can get a good feeling for what kriging is and how it works.